So today we're going to be talking about the three states of matter. Now, can you tell me what are the three states of matter?
Isn't it like liquid?
Liquid's one of them. Good.
Solid.
Uh-huh.
And gas.
Very good. Liquid, solid, and gas. Now, can you tell me what is the difference between these three?
Solids, you can't penetrate them.
Okay.
And liquid, you can. However, we can see it. It's visible. And gas, normally we can't see it and we can penetrate it and yeah, we can't see it.
Okay, very good. So actually, the way I've written these here, I'd actually like to write them horizontally just because I'm going to compare the three of them. So if we've got solid here, liquid here, and gas over here. Can you tell me, imagine that we've got something that can be a solid, a liquid, or a gas, like water, for example. What do we call solid water?
Ice.
Very nice. Okay. Liquid?
Would be just water.
Water. Gas?
Vapor.
Very nice. Water vapor. Awesome. Okay, so let's say we're trying to describe those things. Imagine that you have like a piece of ice. What are some of the ways that you could like measure it or describe it?
We could put on a scale.
Okay, so we could talk about like the mass of it. So I'm going to stop you there because I actually want to ask you about some of the other states with their mass. So you said that solid does in fact, we'll say like, yes, it has a mass. What about a liquid? Does liquid water have a mass?
Yes.
Okay, and if you were to like change it in some way, like pour it out on the table, for example, would it have the same mass?
No.
It wouldn't?
Well, a lot of them would kind of disappear after a while. However, when you first pour it, I feel like it'd be the same mass.
Okay, that's right. So liquid, regardless of like where you put it, it's going to have the same amount of mass. What about, assuming that we've got like a closed room that nothing can escape, if we have a certain mass of water vapor, will that change, or does it have its own mass?
It wouldn't change.
It wouldn't change.
It would have the same mass.
That's right. Okay, so all three of them have a mass, and that mass isn't going to change unless we remove some of it. All right. Okay, so can you tell me something that perhaps solids and liquids have that gas does not?
Volume?
Volume, very nice. I like that. Okay. So first of all, tell me, what is volume?
Volume is like it's usually three-dimensional, isn't it?
Okay, it is three-dimensional.
Height, length, and width.
Very nice.
Yes.
Height, length, and width. Okay, so for example, if you've got an ice cube that is, let's say, 10 centimeters by 10 centimeters by 10 centimeters, so it's got the volume of, 1,000 cubic centimeters, and we take that out of its nice little cube box and put it on the table, what will then be the volume of that ice cube?
It'll still be the same.
Still be the same, right? Okay, so now let's say that we've got that same cubic container, and it contains 1 liter or 1,000 cubic centimeters of water, and then we pour it into a cylinder container. Does it have the same volume?
Yes.
Yes, it does. Okay, so then let's say that we have captured 1 liter or 1,000 cubic centimeters of water vapor, and then we open that into this room that is, let's say, like 1,000 liters, this room. What is the volume of that gas?
We wouldn't be able to measure it.
Wouldn't we?
It doesn't really have a height, width, or a length.
That's true. So when you imagine that, and we open the container. So at first it was actually like a cube because it fills the container, and it was like a measurable volume. So then we open it. Where is that gas now?
All around this room.
Right. Okay. So at first, like right when we open it, it doesn't move at the speed of light, so it would just expand out.
Yes.
But then after some time, when you say that it's filled this room, so what is the new volume of the gas?
This room.
This room, right.
Right.
So what has changed between when it was in the small container and when it was in the large container?
It has a different volume.
Right, has a different volume. So if the volume has changed and the mass hasn't changed, what is something you could say about that gas? Like what is changed for the gas, the conditions of the gas, in the container and then out in this room?
It expands.
So if you took, let's say, something like smoke, for example, that you could see, that it's like a visible gas, and then you open it up. In the container, perhaps it was very, very cloudy, like maybe almost opaque. You open it up, what is it now that it is spread out to the whole room?
You would be able to barely see it, right?
Right, exactly. So you could say perhaps it's become less concentrated. Also, if we were talking about partial pressures of different gases, it would just have a lower pressure.
Oh, right.
Okay, so then, can you tell me anything that gases and liquids do not have, but a solid does have? And I'll give you a hint. So when we were talking about the different volumes, so like changing, like taking the liquid water out of the container, putting it in a different container, or taking the solid ice out of one container and putting it just on a table. That was sort of a hint as to what this third one.
Shape?
Shape, very good, exactly.
Okay.
Shape, nice. So that one's sort of obvious because when we have a cube of ice and we take it out of its container, still a cube on the table. But what if we just, take a cube of water, a cubic container of water, pour it on the table? What shape is it now?
Blob.
Right, it's just like a blob.
Splash, yeah.
And if we pour it into like a cylinder container, what shape is the water?
It would be a cylinder.
Right, exactly. So what is something you can say that is true of liquids and gases, but is not true of solids?
Changeable?
Mm-hmm.
More flexible?
Yeah, they're changeable. And I like the term flexible there. So like what shape are they? Because you can say they don't have their own shape.
Yeah.
So they're always the shape of what?
Their container.
Exactly. They're always the shape of their container. Okay, so now what I want to do is I want to talk about the transitions between these states. So we can erase that there. And if we have like a measure that I'm just going to call enthalpy, maybe you've heard that before. I'm purposely using this one because I'm guessing you don't know what it means.
Yeah.
And so that way I won't be giving you too many hints about why these changes happen.
Okay.
So let's say you've got gas here, you've got solid here. I'm going to put liquid sort of off to the side.
Okay.
But you can see that they generally go up from solid to liquid to gas. All right, so I'm going to give you some really hard questions here. When you go from a solid to a liquid, what is that called?
Melting.
Melting, excellent. Okay, so maybe this isn't so hard. Okay, what about from liquid to solid?
Freezing.
Freezing, excellent. Freezing. Okay, what about liquid to gas?
Oh, I forgot what it's called.
Well, let's say that you wanted to cook some ramyun, so you heat up some water. What does it do?
It boils it.
Okay, and that is one of the two ways that it can go from one to the other. Boiling. I'll give you another hint because I think you know the word. So you talked about the solid state of water being ice, liquid. What was the gas?
Vaporizing.
Very nice. Okay, so this is, we call it evaporation.
Alright, alright.
There you go. And vapor is in the word. And E just means like to or towards.
Oh, okay.
Yeah. So it is becoming vapor. All right. So we got boiling or evaporation. What about when you go from a gas to a liquid? Like the water that appears on grass in the morning, like the dew. That used to be just water vapor in the air, and then it settles down on the grass and becomes liquid. It becomes more dense.
What would you call it?
Well, we've got like the dense thing as a hint. So we've got like blah 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 densation. One thing that a preposition that we use a lot, or not a preposition, a prefix that we use a lot for things that come together, that gather together.
Condensation.
Condensation, very good. Okay. So yeah, a lot of times when you see con at the beginning of the word, it's going to mean like gathering together. Yeah. So like you might have heard of like a conspiracy. Yeah, and spear or spira just means like breathing. So you can imagine a bunch of people just sort of whispering together.
That's conspiracy?
Yeah, that's a conspiracy.
Oh,
So
okay.
gathering together and like whispering.
Okay.
So we've got boiling and evaporation, means going from liquid to gas, and gas to liquid, that's condensation. Now, have you ever seen this one happen? Because it does happen. Or this way.
Is it dry ice?
Yes, dry ice is a very good
Okay.
example. Do you know what dry ice is?
I I don't really know, but I heard it was like not going through the stage of liquid, but going straight away from gas to solid and the other way around.
Exactly.
Yeah, but I never really understood how that worked. But I just kind of knew.
So when people say dry ice, why do you think that they call it dry ice?
I'm guessing because the ice is dry. But how is an ice dry?
Exactly. So you would wonder, like, well, if you've got water and it's getting warmer, if you got ice that is from like water ice and it melts, you're going to have liquid water.
Right.
The thing is that dry ice is not water. Dry ice is made from carbon dioxide. The freezing point of carbon dioxide is around, I want to say, minus 200 degrees.
Wow, okay.
So when you freeze that, you're not actually doing this process. So we wouldn't even call it freezing. We call that, well, the easier one to describe is actually the solid to the gas. When you see that steam coming off of the dry ice, it is becoming gas without becoming liquid first.
Right.
And that one, that's called sublimation. The other one is a little trickier when you go from gas to solid, because in America and in England we have two different terms for it. So I had always, when I studied that in university, it was deposition, which it sounds like just another term you have to memorize, but there is the word deposit in here. So we call it deposition because it forms deposits of something. So if you had like a very cold freezer and there was carbon dioxide in it and you got that down below the deposition point, then you would start to form this dry ice on the walls of it. You would form deposits of dry ice. So it's deposition. The tricky part is where in England they actually use the term sublimation for both directions.
How would you know the difference?
You would have to hear the whole sentence, basically. That's why I don't like that term. But if you were to take like an A-level course or you went to an English university, they would expect you to say something like, when gaseous carbon dioxide is cooled below minus 200 degrees, heated back up, it sublimes into the gaseous form.
Okay.
Yeah, so to me that's a little confusing, so I'll use the deposition. Okay. So we've got lots of terms on here, but we've got at least now terms for both directions for all three phase changes. All right. So can you tell me what is happening when you go from, let's say, a liquid to a gas? Like if you zoomed way in on the actual molecules of a liquid, and then you saw those same molecules once they had become gas, what is the difference in like their surroundings or their behavior?
Is it like heat escaping?
Okay, heat escaping what?
The molecules?
All right, so when we talk about heat, what is heat? With regard to molecules, what is heat?
I have no idea.
That's good, actually. So, because we're going to be talking mostly about the actual particles of gas and the particles of liquid and solid, and their, we call this collision theory, because the whole idea of what temperature does to these different things is based on the particles colliding with each other. So let's say you have solid water, you've got ice. When you look at those molecules of ice, I'm going to represent them as single circles, although you know it's like a 3-atom molecule. Okay, so they're going to be in this lattice that is just, they're all touching each other, and there is effectively no space in between and no room for them to move. Okay. And let's say this was at, we'll say very close to the freezing point. Let's say it's like minus 1 degree Celsius. What do you think is the difference between ice at this temperature versus ice at like, I don't know, minus 201 degrees Celsius?
It'd be more compact.
Okay, actually that's true. It would be more compact at which one of these? The colder temperature, right. Okay, so if it's more compact at this temperature, less compact at this temperature, that means you've got some like gap in between them. Why does that gap happen? Because like the molecules are attracted to each other. They want to stay close together. So what is causing them to be pushed a little bit apart?
The heat?
The heat, right. So at this level, when we talk about heat, we're just talking about individual molecules moving in relation to each other. And that motion is very different for solids versus, say, liquids or gases. So in a solid, you said before that like one definition of a solid is that you can't penetrate it. Another definition is that it has a mass, it has a volume, and it has a shape. That shape is because these are fixed in their positions. But in their positions, they can move a little bit. What would that movement look like if they can't actually change their spot in here? If we were talking about like this guy, this little colored guy. So if he can't move, like change positions with any of these other ones, because that would be like a liquid motion. If he can't move, if he can't change places, how can he move?
Vibrating?
Exactly. So he can vibrate more. And obviously, in order to vibrate more, you need a little bit more space. So actually, that's something that it would be hard for us to measure with just our naked eye, but it is possible to see that ice at this temperature takes up less space, has less volume than ice at this temperature. Right. Okay, so they've started to vibrate more and more and more as we've heated up to here. Now, what happens once we heat that up 1 more degree and we've gotten to 0, and we're starting to go to like 1 degree Celsius?
It'll start melting.
All right, so how will these molecules start behaving a little bit differently?
Maybe hit each other?
Oh, but they're already touching. And they're constantly vibrating into each other. What can a liquid molecule of water do that this guy cannot do?
Change position.
Change position, right. So whereas in this one, he always has the same, like, I don't know, you'd call it address, like relative to his other molecules, he's not going to change position, but he'll vibrate a bit. But then here, if you've got like a liquid, I'll put that like down here. So you've got these guys. They have more space than each other, but they are sort of bumping into each other vibrationally. But now that we've gone just past the melting point, maybe this guy can switch places with this one, and they'll all be constantly in motion, changing places with one another. So if you were to have like a solid object, like a rock, drop into water, it can push these apart, it can move past them, and you can have like flow.
Right.
All right. So then, let's say that you are going from liquid to gas. We can choose either one of these. I don't know. Your pick. Would you like to talk about boiling first or evaporation first?
Boiling.
Boiling. Okay. So boiling happens when we go from, let's say, 99 degrees Celsius to 100 degrees Celsius, and then start to move beyond that. All right. So as we heat it up from 1 degrees to 99 degrees, that would be us like adding heat. You've got like fire under a pot, for example, and you would see the temperature graph just consistently going up the whole time, like 1 degrees, 50 degrees, 90 degrees, 99 degrees, and as soon as it hit 100, it would just stop. You're adding energy, but it's no longer increasing the temperature. So where is that energy going? What is it doing? What is changing once we've gotten to that temperature?
It's boiling.
It's boiling, exactly. So you're still spending that energy. The temperature isn't going up, but you're simply changing the state from these liquid molecules to gas molecules. So what are gas molecules doing that liquid molecules are not doing?
They're leaving the pot.
That's right, they're leaving the pot. So whereas before, all of these were touching, all of them were stacked, they were moving past each other. And at this temperature, they were moving past each other very, very quickly. And what'll happen is once you get them above 100 degrees, then they will start just leaving their friends, because they'll have enough energy to escape. You can think of it kind of like in physics terms, like if you were going to shoot a rocket off of Earth, you need a certain escape velocity. It needs to be going fast enough that gravity won't pull it back. It's very similar here. They need enough energy that the attractive forces of the other water molecules won't pull it right back. Once it has that, it can fly off and it can just go into the room. Okay, so that happens when water is at 100 degrees. Any molecule of water in that pot can suddenly become gas, even if it's below the surface of the water. And we see that as bubbles. And it forms water vapor underwater. Okay, now, the thing is though, if we had that same pot of water here in the room, and this room is, obviously it's a little cold in here, and it's not 100 degrees in here. But if we left it here for a few days, that water level would go down. What happened to those water molecules?
It evaporated.
It evaporated, that's right. So where did they go?
In the room, where they wanted.
Right. So does that mean that the water had gotten up to 100 degrees Celsius?
No.
No. So if we're talking about temperature as simply a way to measure like the average speed of all of the different molecules sort of put together, how does something like evaporation happen if we didn't boil the water? Because the average speed of all the molecules put together is way, way, way below the boiling point. But again, one thing that I'd like to point out, I said average speed.
One of them?
Exactly. So it could be one, but I mean, when we talk about a pot of water, we are talking about billions times billions of molecules in just that one pot. So statistically, even if you just have 1/1,000,000th of 1% have enough energy to just like push right past their friends and just get to the surface of the water, well then they're no longer touching on all sides other water molecules. Perhaps they're only touching on the bottom. And if that one happens to have enough energy to escape, that becomes a gas molecule.
It's like a chain reaction.
Right.
It leaves and then continues.
Exactly. So, and that's also why like the energy that one had, that it had been like distributing to its friends as it ran into them. Now the pot of water has lost a little bit of that energy. So you would have very slow change from a liquid to a gas, just basically because of statistics. Because the average temperature is not the exact speed of all the molecules at the same time. Okay.